Yeah, good idea. Well, I was hoping to do the same, but sort of accidentally, I know I stepped down from head 8 years ago, but then accidentally I had all these students, and it's got bigger and bigger, so I have about 12 people now.
Wow, okay.
And it was like 18 a while ago.
This time?
Oops. Yeah, sure. Well, anyway, you should do a short version of it. Thank you.
Testing. All right. So good afternoon, ladies and gentlemen. My name is Lawrence Yeung, the moderator of this session. And welcome to the TED Talk. And this TED Talk is co-organized by Hong Kong Academy of Engineering Sciences and Hong Kong U Faculty of Engineering. Right? So TED Talk is a series of forums and dialogues given by engineering researchers of diverse backgrounds to share their insights on innovation-related topics. So today, we're very honored to have Professor Ross Murch from Hong Kong University of Science to give us a talk on creating new radio frequency wave technology for 6G. Professor Ross is a chair professor in the Department of Electronic and Computer Engineering and also an IAS fellow in the Institute of Advanced Study, both at the Hong Kong University of Science and Technology. His research focus is creating new RF wave technology for making a better life. That matches perfectly with the title of today's talk. And his unique expertise lies in his combination of knowledge from both wireless communication systems and electromagnetics. And Professor Ross Murch has published extensively in both areas. He's a fellow of IEEE, IET, Hong Kong AES, Hong Kong IE, and recently, in year 2023, he won the IEEE Communication Society Wireless Technical Community Committee Recognition Award. And Professor Murch also served as in different capacities in IEEE and also has been the department head of ECE at Hong Kong UST for 6 years. And Professor Murch received his bachelor's and PhD degrees in electrical and electronic engineering from the University of Canterbury, New Zealand. All right, without further ado, Professor Murch.
Thank you, Lawrence, for your nice introduction, and thank you for coming to my seminar. It's good to see you. So as you know, I'm talking about RF technology for 6G. I've been working on this for 30 years since I arrived in Hong Kong in 1992. So a lot of things to talk about, perhaps. But first off, I would just like to mention that nothing gets done by yourself. I have a fairly large research group. This is actually a photo from last year. And so I have PhDs and postdocs working with me. When I finished my department head, I thought I was going to actually take life a little bit more quietly. But for some reason, this group got big. And so anyway, it's been a lot of fun doing research. I'd also want to thank the Hong Kong government for their research funding and some of my collaborators, both here and in other countries. So let's start. So the wireless world today, we have radio transmitters, TV, cellular systems, Wi-Fi, and so there are many, many radio sources everywhere. And I call this scenario the wireless fog of RF waves. So no matter where you are, where you're going, what you're doing, there's always a radio signal around you. If you go back 50 years, this was not the case, that there would not be radio waves everywhere you go. So you can think of this as kind of like a new resource that it wasn't there 50 years ago, but it is there today. And so what I'm sort of thinking is, what can we do with these radio waves that are everywhere around? And one way to think of it is it's a new resource to be harnessed. And one way to think of it is you can think of sunlight. The sun is a source of radio waves, the very high frequency waves. And for the sun, we use them for camera, solar energy, a heliostat. A heliostat's actually a mirror to light up your room. And then we have sextant. Now we use the sun for navigation. And heliograph, which is mirrors, we use for communication. So for sunlight, we do these things and more already. So these radio waves that we have around, in principle, we can do all those things, plus maybe more. And so I guess I'm coming from the perspective of attempt to do the same for radio waves. So not just for communication anymore. Now we all know how to do wireless communication. But can we do some of these other things, like imaging on a bigger scale? And can we do even energy harvesting with these radio waves? And it could provide new industries. And the big thing is that creating new RF wave technologies for 6G. And in a minute, I'll talk a little bit about 6G. And one of the visions is 6G is no longer just a communication medium, that it will be something bigger. And it sort of ties nicely with this. So the approach is I look at it holistically, and I think of these RF waves as a new resource, and I split it into wave shaping, wave sensing, and wave characterization. And so if we can shape the waves, then we can use them for our own purposes, for communication. If we sense them, when these waves go through us, we can do imaging. And if we can characterize them, we can do the first two systematically. And so these are the fundamental building blocks that I will talk about. So today's talk target is new RF technologies, and basically the scope is leveraging existing wireless systems to see if we can do a little bit more than just communication. And as I said, to put it in perspective, 6G is, everybody's talking about it. I know we've just got 5G. So there's a lot of proposals and discussions by different groups around the world. This is a white paper just at the end of last year by Huawei. But you can see sensing becomes one of the topics. Energy efficiency, battery life, very high density. These are things that involve more than just communication. And the reason we need 6G is that 5G cannot support what's coming in the next 10 years. So if we are here, the total data traveling through the network is maybe in the thousands of exabytes, but in 10 years' time, it's going to be 500 exabytes, and 5G cannot handle this. And so, yes, you may think, why do we need 5G? But just this, we're going to need something new in around 10 years' time, no matter what. So that is what we're planning for now. So continuous innovation is needed for wireless communications, and it's quite unique in that it's always growing at quite a fast rate. So you may think, oh, wireless is old stuff, but it has to be continually innovated and extended. And there's an interesting paper, some other predictions. They use this term here, TK mu, and it's a sort of saying that it's abbreviation for the latency is to be very low in the microseconds. The bits per second per hertz should be 1,000, and the T, actually I forgot what the T is, maybe that's terabits per second. And so this TK mu is the abbreviation for all these, the target. Okay, so that's a little bit of background. And so now I just want to talk about three things that we have done and 3 prototypes that we have worked on among my group. And then at the end, I will talk a lot about some more exciting things that we can do in the future. So I start off with wave sensing because it's very different from communication. And it turns out I did my PhD in inverse scattering, which happens to be imaging. And so when I came to Hong Kong, the wireless revolution just began, And a company called Hutchison Telephone came to our university, which had just started, and said, we'll give you a million Hong Kong dollars to work on wireless. And so we had a group of 8 people. None of us were wireless. I guess there weren't wireless people around the world. And they said to me, you have to handle it. So I changed quickly from imaging to wireless. That's why I have this combination of wireless and electromagnetics. And so that's why I have this knowledge from 2 areas. So that's a nice thing about going to new places and having new experiences. So what's RF imaging? So the first thing to remember, it's device-free. So I can do the imaging even if I have a mobile phone or Bluetooth on me or not. I don't need any other sort of device on me. So device-free is the key word. We have many conventional approaches, radar, LiDAR, and in 6G, the proposal is we'll combine imaging with communication in some way. So the idea would be radar and maybe communication together, and so we could do imaging. So can we do better than this? So imaging is a general technique. It's known as inverse scattering, and signals passing through the objects like this, they get changed, and we measure the changes, and then we work out what that object was. So tomography, you go to a hospital, get a computer tomography, MRI. These are all known as inverse scattering. And we can use reflections like radar, but that's only half the story. The waves are also going through. So radar, can we even do better by getting the waves going through it? And why is imaging hard? Well, I have tried to avoid as much maths as possible, but I do have this one equation that you'll see 2 or 3 times. And let's start with the picture. Imagine this is a transmitter. This is an object, and we are receiving waves. Then in this equation, this is the measurements. This is the object, and this is the waves going through the object. And the reason why it's difficult is because we only know that, and we don't know that or that. So there are 2 things in the integral that we don't know, and that's what makes it difficult. So it's an ill-posed problem, and both the field and the object are unknown. And the other thing is, this is, 2-dimensional? This is 3-dimensional, so the measurements are 1 dimension less. And even if I take more measurements, it doesn't help because it's still 2-dimensional. So it's also a very difficult scale. Now we can image the galaxies, DNA, our bodies, the Earth, but it's actually quite difficult to image the scale of buildings because the wavelength of the building stuff is similar to the object sizes. So this object size is also very difficult. And so this is why imaging is a tricky business and why it's not done normally. Okay, so you're also welcome to ask questions along the way if you have some curiosity on some aspect. So there are existing methods. We have linear approaches, nonlinear, and also some ad hoc kind of heuristic approaches. And so I won't go through these approaches. But we are proposing a new extension here that we call this right-off approximation that we want to use. So let's just give you an idea. We have a building like this, and we want to image, say, 1 floor of it. Then we could take a cross-section like this. There are chairs, furniture inside here. And then we could put transmitters and receivers around it. And for example, transmitter, we could measure the field at the other side. And the inverse problem is, now estimate things like, this is permittivity, so it's sort of like refractive index. And we're using this equation somehow. So we have that again. So I'll go through some of the key concepts in a minute, but these are some of the experiments that we have done. So we have a lot of transmitters and receivers. I know it's not practical, but it's just a first step. And we can image the body, the water, and the books. And it's more than just the location. We can actually say the permittivity of this is different from that and different from that, which have not been done before. And even here, we can find those books in that thing as well. So we just use very simple boards. No, these are ESP32 Wi-Fi boards that you can buy for 20 or 30 Hong Kong dollars. We've modified it, put a little bit of a bigger antenna on. And if you just take the books and the water, this is the ground truth. This is simulated, if I use simulated data, and this is if I do the measurements. Now you can see it's got roughly the right places, but the key thing is it's telling us that the two materials are different. That, okay, this is high permittivity and that's low permittivity. And that has not been able to be done before. So with this technique, we're able to gather more information. So the idea would be, can I combine it with something like radar to have like a multimodal sort of imaging technique? And even here we have a person, so same thing, get the same type of result. So we get water, books, and person. And we can see that they have different permittivities. Okay, so that's what we got. But yeah. Yeah, a lot. So I think there are probably here, I think it's either 20 or 40. It looks like 40 there. So it's a lot. However, the challenge, that's to prove it, the proof of the concept. The challenge is to get it now less. And so you can imagine if I have radar, and the radar would say roughly estimate some of these materials, then I would need far fewer of these because there'd already be a lot of information. And so if I combine radar with a few, maybe a lot less, then I can probably do the same. So that's a good question. There are other things you can do too. So I won't go through the math too much, but the traditional approach is we do some approximations and we actually get rid of some yucky terms. No, you probably can remember grad and stuff like that. We get rid of these terms to make it easy. And so this is the traditional approach. And in our approach, we try and somehow do a better job of that and get a better reconstruction. So the traditional approach, when I did my PhD and someone asked me, could you image a water bottle and a person? I would say impossible, absolutely impossible. But with this thing here, it is, for me, it's quite a significant step forward. I didn't work out the theory. I had a PhD student who did it for about 5 months, and he came up with this. But the key idea is this. I have two materials on a plane. This is a lossy material, has some refractive index, and a lossy component, and this is air here, no free space. And then I have a wave coming in. Then I will get a reflection and a transmission. Now, by Snell's law, I think we'll probably remember from high school, says that the incident angle times equals the refractive index times the transmitted angle. But the problem here is that this is complex. And so if it's complex, these would be complex angles. So Snell's law is no good. So they didn't tell you that at high school, that Snell's law is no good. And if you look through the literature, there's just a handful of papers that handle this particular situation. And the way to handle it is that you split it into two waves, a refracted wave like this, but also in addition a sort of like an attenuation wave. And the attenuation wave just attenuates in this direction, so it's as you would expect, but the wavefronts still go in that way, but it gets attenuated. And this is quite a nice thing because the direction of this loss component doesn't depend on the permittivity. So no matter if the refractive index is high or low, we always know that this wave, this attenuation, we're going in the same direction. So one of the reasons why imaging is difficult is because if the refractive index changes, this thing will also change angle, which makes this thing much harder to do imaging with. But if I already know that it's always in that direction, then I have some information. And this is what we use. By using that information, we can get a better estimate of the permittivity. Okay, so I won't give too much here, but it happens that these yucky terms cancel out if we do this, and we can actually image this quantity, which is the permittivity of the real part and the imaginary part, and so we get this estimate. The other thing is it's a linear method, and linear methods are always very nice because if I add an object to the thing, I just get the two objects added together. So this is not true of electromagnetics. If I have one object and two objects, they will interact, and it's not a linear problem. But in an indoor environment, everything is far apart. Typically, it is linear. And the reason it's nice if it's linear is because if I take a measurement, say, with nobody in the room, then I take a measurement with people in the room, and I subtract it, then my method will tell me the difference. So I'll be able to image the changes in the room. And the reason why that's important is because you can imagine if I send waves through this room, the scattering will be incredibly complicated. There's no way I can image the walls, the windows, the camera, the chairs, the people. So by subtracting the two, I get rid of all that stuff, and I can just image the people, the change. And that allows a huge simplification. And you cannot do that with other techniques. So also a big advantage of this. So these two things combined, this subtraction thing, this new way of looking at the waves passing through, allows us to get a good image, even in a complicated environment, by subtracting the two things. Okay, and so in the end, what it's become, as always, everything always comes down to solving a linear equation. No matter what, if you're doing civil, mechanical, chemical, electronics, whatever, in my experience, it always comes down to a linear equation that you solve. So once it's a linear equation, we can use all those tools, and we get these results that I've already mentioned. So the one here I haven't shown yet is we actually have the transmitters around the outside and the books there. And so, of course, this is very complicated. But if I just subtract the waves with the books and without the books, then I can image the books, even in a complicated thing like that. And so I think this technique is quite interesting. As I said, it's not really been done before quite like this. We've also got a lot of simulation results. There is also an ad hoc technique that computer scientists work out that they use, which they just developed because it looked like it was a good thing. And it also works very good for objects. And it turns out that our technique can explain why that works so good. And you can see that our technique also gives a better reconstruction. So it also gives some information about other techniques that have been working pretty good. So one aspect is how well does it work? This blue curve here is the ideal result, and this is permittivity. So typically, like a permittivity of 10, that's a lot of scattering. Permittivity of borders here, pretty high. So it works up to about permittivity of 10. It still can identify the material. It's still monotonic. It's just that it won't give you the right answer, so you have to scale it a little bit. And so typically in the past, most inverse scattering or imaging things would only work for permittivities down here. So no way would they work way up there. Okay. So we have quite a few publications over the last couple of years on this that have come out. So the Bill's question here is very relevant, and the first thing everybody asks is, can you have less transmitters? So our next step is multi-mode imaging. So combine it with another technique, such as radar and or LiDAR, And so we get reflection-based imaging, which is easy to understand, and then we combine it with transmission-based. And then that should cut down the number of measurements required, and we can estimate all those parts of the indoor situation which can't get accessed by LiDAR. We can also use permittivity, estimate the permittivity. The method is also different. A radar is wideband, this is single frequency, so there's a difference there, and ultimately reduce the number of nodes. So extend to 3D, integrate with 6G, can we add phase and frequency? Okay, so I have other stuff to talk about, but this is the first bit, the sensing, if you would like to ask a question on this part so far. Yeah.
Ross, I'm not really a few. I just want to ask some very naive questions, right?
Good.
So for radar, the bandwidth kind of related to the accuracy.
Yes.
If for your case, you use single frequency, where's the accuracy coming from?
Yeah.
From the number of spatial nodes?
Yeah, so with radar, as you say, it's the bandwidth. If I want to get resolution of a few centimeters, I need a huge bandwidth. And so in practice, radar is good, but the resolution you need is not practical for civilian applications because I'm going to need a gigahertz of bandwidth or more to get a resolution in a room scale. So principally, it's the wavelength of the radiation. So it's like the diffraction limit that you would have learned about in physics, that if I have two slits and they're half a wavelength apart, then I can resolve them. So the wavelength at about 2 gigahertz is 10 centimeters or so. So with this technique, I can get to resolutions of at least 10 centimeters, which would be like several gigahertz in terms of radar.
I saw that you put a lot of
Yeah, that also helps give us more gives us more information, but it's yeah, but it's not only that, it's the wavelength that really does this. But of course, all these measurements too. But if the wavelength was low, it wouldn't help in that case. Yeah. No, when someone in the audience says, I've got a simple question, the alarm bells go off, that's going to be the most complicated question to answer that you'll ever come across. It's the simple questions that are the best questions.
So the message you presented requires some kind of room calibration.
Yes, that's the other thing. Normally, say, if you do computer tomography in the hospital, you'd have to calibrate the whole system first. So no one would be there, and then you would calibrate it. All the sensors, the losses in the cables, everything would be calibrated. So the really nice thing about this is because of that subtraction thing acts like a calibration. And so this is like this is like a reference, and then I subtract the two, so all the losses, all the other stuff automatically gets cancelled out. And so then I'm really imaging the difference. So it's kind of like self-calibrating. And so this is what's nice about the linear thing. If we use some of these advanced nonlinear techniques, even AI techniques, there's no linear relation, and so I can't do that subtraction. So this is why this is really nice to have that linear part. So a great question. Okay, great. Perfect. So I know you only have if I talk too much, you're going to fall asleep. So the good news is this section is quite short. This section is a little bit shorter than that section, so you're already on the home straight. So the other part of this, I was talking about wave sensing, is imaging. Wave shaping is, I'm trying to shape the scattering environment so that I can do more with my radio waves. And one of these things is known as reconfigurable intelligent surface. So we've also looked at this. And the idea of this is that, say you have waves coming into a wall, and maybe if I can control the wall, I can get the waves coming out, or I can do focusing, I can do all sorts of stuff. So the last 2 or 3 years, there's been, I think, probably thousands of papers written on this from a system perspective. So it's a good concept, maybe not the most practical of concepts, but not so many people have made prototypes to show you could do it. So we made some prototypes of these surfaces here. And what we have done is, we have a surface like this, we make many, many elements, and then we adjust these elements, and we can change the scattering of the wall. So the idea would be that I change it in such a way that maybe my communication is better, or I change it in such a way that maybe my imaging system is better, or I can use it for better location, this type of stuff. So these are all the reasons why people want to use it. And these are some scenarios of potential applications. So for example, if for some reason there was a blockage, I could change the environment, put it there, and I get this reflected path. And other things, I can do physical layer security, more high density of users, and so on. So as I said, there are thousands of system papers that just make some assumption. Okay, we have a reflecting wall that we can change, and we can do all these things. But how to make this wall practical? So one of the big problems of using this technology is that, principle, this should be easy to make, but it turns out it's quite difficult, and therefore there's a bit of a hold-up on using this technology. But let me show you what we have done. So what are the challenges? There are lots of system results, but we need wideband designs, wide beam, how to control the elements, how to do channel estimation. And just to give you an idea, imagine this is your surface. That could be the wall. And then on the surface, I have many little elements on there that I want to control. And if I control their reflection characteristics in the right way, then I can make a beam go one direction or another direction, or whatever I want to do. So I use this term separatal systems, which means that the characteristics of the waves coming in and the angles and the waves coming out are independent of the sort of the status of these elements. And then I also define another system which is non-separable, that everything depends also on the states. So this is a little bit more complicated type of system. So there's two sorts of surfaces that you could have. The first type is probably better. And I won't go through the details too much. But one of the other big issues is channel estimation. I have many, many elements on here. I need to estimate all the channels going to these elements. And so we have a big estimation problem too. So non-separable systems probably would be harder to do estimation in than separable ones. But anyway, that's a little bit of background. We have two proposed designs here that we have worked on. They're different in the sense that this is a passive one. Waves come in, we just change the structure, and the waves get reflected, and we can control the environment. So no energy is used here. In this one, waves come in, they're amplified, and they get reflected back out. So it's an active surface, and so this could give us 10 dB gain. So they are two different types, and I'll go briefly into how we make them. We have published both of them over the last 2 years in transactions on microwave theory and techniques. When they first appeared, they were in the top downloaded list, in the top 10 for 2 or 3 months. So they're quite a hot topic. I don't know if these designs are particularly great. It just happens that we were some of the first ones that were able to publish it, I think. So this is the first one. And so you can think of each of these as an element, and on each element we can have 4 different phases. And so if we have 4 by 4 elements here, we could form beams in different directions by changing the wave phases. So it works at about 3 gigahertz, and it works for large incident angles. And if I take one of these elements, and so this is about half a wavelength, and then inside the element, I show you what we have inside. Then we put some switches. So 4 switches, which change connections between these elements. And when I change the connections, the reflected wave will change phase, and then I can control this surface. So the switches have a circuit like this when they're off, and a circuit like that when they're on. And when I change those characteristics, I can work out how the phase will change. So you may ask, no, how did we find those connections and locations? Well, we just do it by optimization. We can have a very efficient formula to work out what the reflected phase would be. And then we can just sort of search. Well, I put switches there, I put connections here, until I get what I want, and I can design it. So we did an optimization, and we designed the proper locations. So just a few other little things about it. So this is the surface. So we have 4 by 4 elements. And inside one element, we have this structure of the 4 switches. So this is the front side. On the back side, we need to control these switches. And so for each element, we need to have 4 control lines. And so you can imagine if you have a big surface, you need a lot of control lines. But the moment you put in a straight wire in electromagnetics, it destroys all the scattering. And so what we do, so these are DC switches, and so they just turn off and on with a DC. So these work at low frequencies. These are working at 3 gigahertz. And so we have to make these things invisible to RF. And so these wires actually have inductors in them every centimeter or so. And so in the one wire, it has maybe 10 inductors. And so at DC, the inductor is perfectly fine. It conducts perfectly. But at RF, the inductor is effectively open circuit. And so the RF doesn't see it. So behind here, I have these structures. It controls the switches with DC, but the RF is completely unaffected. So it's kind of like we have some invisible wires at the back. And so this is a key thing. Whenever you put wires in RF stuff, it will affect things. So this is the actual prototype, the front side, and then the back side. And if you look carefully, you can see all those inductors that we've put into it. And you can see this is just 4 by 4, and the actual size is about that actual size. But sort of the dream of a surface is it would be the size of that, or the size of the back window. So you can imagine that would have like 100 by 100. And you can imagine the number of wires that you would need to control it. So now immediately you think this is not practical. But anyway, that's what research is. There was some hurdles to overcome. One of them is a huge number of control lines. So we've put it together, and that's the surface there. And then we have a transmitter and a receiver. So just to prove the concept that normally with a mirror, the wave goes in and the wave comes out at the same angle, but opposite direction. But because we can control the phases, we can control the reflection to be at any angle. And so it's a mirror, but we can completely control the angle. And so no matter what this angle is or this angle is, we can find a combination of phases that make the two maximum. And these don't mean much to you, but this is it's kind of like the reflected wave. And so we were able to change it to be like minus 30 degrees, 30 degrees, 50 degrees, and we get about, 10 dB gain with that little surface. So it sort of shows proof of concept that with this surface, we can actually control the environment and get, even with that simple surface, 10 dB gain in our system. So this actually turns out to be a non-separable system. This idea of separable and non-separable, we haven't thought of it before. It was only when we made it, and then after we made it, we suddenly realized, actually, it's not going to, doesn't fit the conventional model. And so it opens another door to some other things. So just quickly going through the other one. The other one is the same idea, except it also amplifies. So signal come in, signal go out, and we change its phase. So we need some microwave circuits and work out some special things. It's a special amplifier because normally you have an amplifier in, out. But here that's going in, reflected, and then back out. And so it's hard to get the isolation between them. So you have to be very careful with matching. So the matching has to be pretty precise. and so on. So it's not trivial to make it. And so the gain of this thing can only be about 10 to 15 dB, and then it's too hard to make it better than that. So we've also made it and tested it. Same thing, compared to the passive surface, we get about 10 dB extra gain. So if I put that on I can do that. So key point to note, the second one is a separable surface, and so that's what we've done for that. So next steps, we need to understand this issue of separable and non-separable, channel estimation, and how to combine it with imaging. There are also some more advanced surfaces which let the waves go through the wall, and some reflected as well. Okay, so that's the second topic. So if you have some questions, this is a good time to ask. And the next topic is quite fast, so I've nearly finished. So one thing about this, as I said, there's a huge amount of interest. There's around the world, especially in universities, many people are publishing papers, and you see keynote talks and so on. But industry is holding off from it because I guess they've tried to make it, and they've come to the conclusion that it's extraordinarily complicated, and so it's certainly not on their, I don't think it's on their immediate horizon. But that's what research is about. Maybe it can be useful for some other thing. Like in certain situations, it could be useful for imaging, or it could be for location estimation, some special application. I don't think it would be used commonly just because it's going to be too difficult and expensive to make. Yeah.
I just have a quick question. So for RF imaging, it's active devices. You need to capture the signal, right?
Right.
For the RIS, I understanding is a passive devices. So how do you combine them? And in what sense?
Yep. So the original concept of RES was that it was passive, but recently there's also been active ones where the things actually also amplify. So the idea with the if it's passive, then I would still have a transmitter and a receiver, except now I would have another mirror, and then that extra mirror is like giving me additional information. If I change the mirror, then my scattering would change. And so one way to get over the idea of having less receivers, transmitters, is to use a surface, and I just change the surface, get different reflections on the surface. So it's like giving another path through the environment.
How does it help the imaging? Does it improve the imaging?
Yeah. So just imagine normally, say, the very simple idea is that if I have a wave from here to Doug, for example, then it will get blocked by the person in front, and then we know, okay, I've got some information. I know there's some attenuation there. Kind of that's like imaging. But now if I have a mirror over there, this wave will also go to there, and that way. So that's like another path, and I'm getting more information about the attenuation through you, and maybe Justin going to Doug. So that's how it is. And then for other people, like there would be a clear path, like to Bill, and then there's no attenuation there, and then. So it just gives you more information. So you can think of it like that. I had the linear equations. I have this many linear equations. When I put that surface in, I get this many linear equations, is another way to think of it. Yeah. Very good. Okay. So last topic, just more of a fun thing. Though IoT is an important area. Now there's going to be billions of devices wanting to load information to the cloud. So one of the issues is, how do we get energy to them? And this part here, the goal was, can we use RF energy? Remember at the start I said the sun has solar energy. Can we use all those waves to collect the energy and power up the circuit? So we have developed energy harvesting with RF waves in the environment. And so what we have done is we have antennas, we have rectifiers, combining, and then we use off-the-shelf power management unit. Now this is where you have your capacitor. Then I would have my Bluetooth transmitter and sensors, and then this would talk to base station. So the thing that we're good at is designing multiple antennas. And so traditionally, most people would make these things with just one antenna. And so what we've done is we've used many antennas in a compact area to try and get more energy. And this is a prototype we have made. It's not small. However, given the challenge of this, it's actually working, which is quite a hurdle. This is at a university, and this is a window. And there's a courtyard, and across the courtyard, there happens to be a base station up maybe 50 meters away. So it's like we're here, and maybe across 50 meters away, there's a base station. And then I put our energy harvesting unit. So it's like just ambient waves around us. The source is completely uncontrolled. And I have antennas on there, about 16. And so it's collecting the energy from those waves, just from the base station. And then it charges up the capacitor, and then about every 10 minutes, it can collect enough energy to sense temperature, air pressure, and humidity, turn on a Bluetooth transmitter, and send the information to a server, and it can collect the information. So there's no battery on here. It's completely self-powered, but for just RF waves. So the amount of energy you get from RF waves is tiny compared to sunlight. So if it's daylight, it's better to have solar cells, of course, because you collect more energy. But if for some reason, with solar cells, they always need to be visible. So like if you're going to use solar cells to power up your IoT, say in here, you'd have to have the solar cells visible on the walls. So you may not want that. You could use this. Now, they could be hidden because the RF waves would go through the wall. So it has maybe some limited applications in some certain things. And one other area is, well, here it's not controlled, but we could also set up our own source, and we could just shine it to there and power up the thing as well. So this was a master's project that we have, and the Hong Kong government also has a IoT initiative. So we also made one of these for them as well, to work outdoors, just to show the concept that it's possible to have self-powered IoT based on RF waves only, so mainly from the wireless waves. As I said, the power is really low, so it's of the fractions of microwatts that you're getting. So the power you get is pretty low, so that's why you need to store it for 10 minutes or 15 minutes. Okay, so we have also published that. We have many different types of antennas for this energy harvesting. In my office, I actually have, I think 4 by 8, 32 antennas mounted on my wall. And in my window, there's actually a base station maybe 100 meters away. And we're using these antennas to be a self-powered IoT sort of energy harvester based on the base station outside as well. Anyway, I'm not sure if it's practical or not practical, but we can certainly show you can do it if you have enough antennas.
Sorry, Ross,
Yeah.
and these are rectifying?
Yeah, they're rectifying antennas. So the key thing here is that if I just have one antenna and I receive it, the RF energy you get is really low. And so if I put a rectifier on just one, the rectifier won't turn on because the energy is too low. So some of them are connected RF together. So I join, say, 4 or 5 or 8 antennas together at RF, and then I do the rectifier. So when I have the 8 antennas connected together, I'm getting 9 dB extra energy. And so it's a sort of hybrid combining. So some RF combining, and then some, and then the rectifier. So for this one here, for example, there are actually only 2 rectifiers, although there are 16 antennas, just 2 rectifiers. So yes, it's a rectifying antenna, but not straight antenna rectifier. Okay, so that's just sort of a snapshot of 3 things that I have done the last few years. So is that all? What else? Some other topics I think are pretty interesting are this thing, space-time, electromagnetics. some of the things you could do with this maybe you can make the antennas change with time. And if you make them change as fast as the symbol rate, that maybe you can simplify the RF transceivers and do some other stuff. There's another topic called fluid antenna systems. In fluid antenna systems, it's about an antenna that changes shape. In fact, you can think of it as a moving antenna. There's a lot of system results. The idea is this: say if I have a receiver and there's multipath around, and there's a base station A and a base station B. So the signal that I will get if I move my antenna through the environment like this, I would get some kind of fading signal like that. But because the other base station is somewhere else, the other base station's fading envelope at the mobile would be like that. And if I could very finely tune the position, I could find a position where base station A is good, base station B is faded, and I could get sort of multi-user improvement. So this is the idea of FAS. So it's proposed by a professor in UK at UCL, Kit Wong. So he's a system person, and so they have made antennas with liquid in them, so they physically move them. But when you physically move material, it's too slow. You can't change it at a high enough speed. So you need to make antennas that can do this, but at high speeds, at millisecond speeds. You know MIMO. So MIMO antennas are still a big thing. So there's a lot of design things to be done on MIMO. One of the things is how many antennas can you put into a small area. So for this one here, there are 21 ports in this design. Ambient backscatter, and then there are the things that I mentioned as well, imaging, sensing, and reconfigurable stuff. So because wireless communications, it's gone through several generations, that to get the necessary bit rates and performance, every little bit of technology you can possibly get from all different areas needs to be applied. And so that's why I think electromagnetics is now being leveraged in a much greater extent, is to try and get that little bit of extra performance so that in 10 years' time, it can meet the demands of wireless communications. So I feel there's a little bit of a rejuvenation of RF technology from the perspective of trying to extract more performance for wireless and other things. So key points to take away: RF waves are everywhere, and we can make use of them. We can harness them for 6G wireless, create new breakthroughs, and here's a list of things that we could be doing. I'm not sure if any of them are going to be important, but maybe some of them will be. We never know. And as I said, I think it's very important to have an understanding of both areas. And in today's world, in IEEE, there are two societies: a wireless society, communication society, and antennas and microwave societies. And of course, completely separate. And to do this stuff, you need to know about both, because some things you assume here are not good for wireless, and some things assumed in wireless are not good for electromagnetics. Anyway, that's all I have to say. So thank you. Intra. I guess interdisciplinary would be like EE and humanities, but this is within the discipline of EE, so inside. Intra. Maybe I'm... With it, is it inter within EE? So I thought inter would be from EE and something else. Anyway, maybe I have it wrong. Of course, yeah, of course. The energy is disappearing. I'm using it to power my IoT, yes. So my neighbor next door if the waves come in here and I'm harvesting the energy, my neighbor won't get any coverage.
And the second question is, you did not talk about
Materials, right.
They will add another dimension.
Yeah, especially for the reflectors, the metamaterials. I guess metamaterials are another area of electromagnetics where you use very small structures, less than a wavelength, to create new characteristics. So metamaterials have been used for making a lens at RF, so I have an antenna. In satellites, for example, they need to have a directive antennas, so they can use metamaterials to make the beam change more easily. So there's a lot of applications of metamaterials. The thing about metamaterials is that they're hard to reconfigure because there are so many elements. So I haven't discussed them here because just typically metamaterials are used in special applications. They're pretty interesting things, but they are a bit difficult to reconfigure. Okay, very good. Thank you.